Hello, dear students. Welcome to the class and welcome to the channel. Very welcome to this very special video, which is not part of any of the playlist which we are continuing right now. Maybe if I get better response, maybe I will add it later on and will create a new playlist if you all insist. But today's class or today's laboratory session, we are going to discuss about few things which we have discussed earlier, like we are going to perform some practicals related to the power system. Now remember, we have discussed about the modeling of transmission line. We have discussed about the uh, how we get all abcd parameters and how we set up the pi type of medium transmission line. We have discussed about how we get t analogy or T topology of transmission line and what are the parameters related to it. We have also discussed about the symmetrical components and unsymmetrical components in its own playlist in detail. So today we are going to discuss about the practicals of it. So first six practicals we have discussed earlier in the previous lab session videos. See, these were the first six practicals. Last was the per unit system. So we have covered all till then in the previous section, and today we are going to focus on last remaining three last practicals, 7, 8, and 9, which will include basics of uh, the transmission line fundamentals, the modeling of transmission line, and we are going to see stuff. Most of the time we are going to see the stuff related to the modeling symmetrical and unsymmetrical system components of or symmetrical or unsymmetrical components of my power system. So first we are going to see the MATLAB program for the calculation of symmetrical components for unbalanced vectors. So unbalanced vectors are none different than the vectors we have discussed earlier in that playlist: zeroth sequence, positive sequence, and negative sequence. And if you remember, each of the components, zeroth component, first component, positive component, and negative component, all three of these components have had uh, separate formulas for them, right? For the voltages, VAVB and VC, VAVB and VC, VAVB and VC, and how they are different, what is the sequence, how they differ from each other. If you want to find out, please check out the videos, the whole playlist. Link will be flashing on the top right hand side corner of your screen, which will lead you to that playlist, and you can check out the whole playlist. I've discussed everything in detail over there. So without wasting any time, let's get started. The first practical, the seventh practical indeed, is discusses about the MATLAB program for asks us to write a MATLAB program for the calculation of symmetrical components for unbalanced vectors, right? And symmetrical components for unbalanced vectors are nothing but positive sequence, negative sequence, and zero sequence components. So we have to find out the components. So again, the code, I have already completed the code. I have written the code in the MATLAB. By the way, I believe you are uh, well aware of the different tabs and different functions of MATLAB. I assume you all are aware of the basics of the MATLAB as well, so I'm not going to uh, teach all that thing again. If you want to know the basics of MATLAB, I have covered it in the previous lab session video. In the initial part of that lab session video, I've discussed about the basics of MATLAB and how MATLAB works, so you can check it out from over there. Now we are going to discuss only about remaining three experiments. I'm not going to explain how MATLAB works. If you want to know that, you can check that out as well. I will give the link of that previous lab session in the description, and probably even on the top right hand side corner of the screen in I button. So the seventh experiment asks us to give the um, zeroth sequence, positive sequence, and negative sequence values of a vector, right? So here we are having a code for it. So first is a CLC. I've told you what CLC does. It simply clears the screen or clears the command window for me. This here is the command window if you are unaware of it. Then what we will do, before we take input from the user for the value of the voltages, for the value of phase voltages, phase voltage A, B and C, or R, Y and B, however you want to take it. Before that, remember, we need the value of alpha. We need the value of alpha. And if you are not aware of what alpha is, please check out the videos in which we have discussed about the derivation of all these components in detail, which includes positive, negative and zeroth, all three type of sequences. So the value of alpha has already given to us in the question itself, and we have taken the value of alpha is as given here, right? Minus zero point 0.5 plus j into 0.8666. Now we will ask the user to provide the input for the phase voltages, phase A, phase B and phase C. So phase voltage inputs are VA, VB and VC. These are the variables, and they are given using this statement, or this one line code. VA equals to input slash n is for new line, enter the value of phase A voltage, which will ask user to enter the phase A voltage. VB will ask the user to enter the phase B voltage, and VC will ask the user to enter the phase C voltage. Now once we have values of voltages from each of the user, what we will do, we will calculate the zeroth for positive and negative sequence components. So remember, what was the formula of zeroth sequence component for VA0, VB0 and VC0? All three of them were equal, all three of them were similar, right? Yes. And the formula was VA0 equal to VB0 equal to VC0 equals to 1/3 VA plus VB plus VC. It was as simple as that. No complications involved, right? So we simply took VA0 equals to 1/3 VA plus VB plus VC, and then we took two other variables as well, VB0 and VC0, and we made them equal to VA0, which means the value of VB0 will be equal to VA0 and value of VC0 will also be equal to VA0. Then we have formed a matrix, because remember, we whenever we write the value of zero sequence, positive sequence and negative sequence voltages, currents or anything, any components or any quantities, we always present them in a matrix form. So you have to form a matrix. So we have formed a matrix here. The results of zero sequence will be equal to VA0, VB0, VC0. That will be my matrix. Now I have acquired the matrix. All right, I have acquired the matrix. And if you have seen the previous lab session, if you were uh, there, if you have attended that, then this line 12, the code of line 12 will only give us the values, but it will not print it. It will give the key, it will give the values in the workspace in the form of this variable result underscore zero sequence. But now I want to print it, right? I want to print it in the command window. I want the results. So for that, what we will do, we will use this function, disp function. Disp the result of the zero sequence is, and then I have just displayed this variable itself. Now you guys might have a question that why we are not using fprintf statement. Previously or up till now we have used fprintf statement everywhere whenever we wanted to print the results, right? But no, fprintf will show an error if you try to run it. Why? Because fprintf will not support the matrix, right? Fprintf does not support the matrix formula, and that is why we are using disp function here. Same ways, now let's go for the positive sequence component. Now we have plotted the values of zero sequence component. Let's try to find out the value of positive sequence components. So remember, for positive sequence we used to take VA1, VB1 and VC1, and the formula, the matrix of VA, this positive sequence component, was one third into, what was the value of VA1? VA plus VB into alpha plus alpha into VC square. Remember what was the formula of VA1? One third VA plus alpha into VB plus alpha into VC square. Then again VB2 was the alpha into simply VA1, and VC1 was equals to alpha into alpha square into VA1. And if you are completely confused about how did these values came and how did we got these values, please follow the lectures, or maybe I can show you the show it from the PowerPoint presentation I have made. Just give me a second. Okay, so see here, you can see the formula of VA1, one third VA plus alpha into VB plus alpha square into VC, and the another formula which we have discussed is here: VA equals to VA, VB equals to alpha into VA, and VC is equals to alpha square into VA. And that is what we were discussing right here. See, one third VA plus alpha into VB plus alpha square into VC, and VB is equals to alpha into VA and VC equals to alpha square into VA. So these are the formulas. Then again we will print the results in the matrix form, and we will save it into the variable named result positive sequence. Now again I want to display the results in the form of this result positive sequence. So let's display it using this formula again. Result for positive sequence is, and we will simply display that variable itself, and it will give us the positive sequence vectors or positive sequence component for these voltages. Now we move up to the negative sequence components, VA2, VB2 and VC2. And uh, just like positive sequence, the negative sequence was same, almost similar to the positive sequence, but the power of alpha used to get changed. So VA2 will be equal to one third VA plus alpha square into VB plus alpha into VC. See here, VB was getting multiplied with alpha. Now we are getting alpha square. We are having alpha square getting multiplied with VB and alpha with VC. And then VB2 will be equal to alpha square of VA1, and VC2 will be equal to alpha into VA1, which will give us the negative sequence components VA2, VB2 and VC2. And we will save the results in the negative sequence. We will save the result in the matrix format, and that matrix will be saved in this variable. You can see result negative sequence VA2, VB2, VC2, and then we will display the results using the disp function, just like we did with the positive sequence and zero sequence. Now let's try to run the code and let's check if the code works or if it does not work. And if it does not work, then what uh, uh, what corrections or what updates we need to make, right? Let's see. Go to the editor here and just simply run the code. Okay, he is first asking us for the value of phase A voltage. Now for the simplicity's sake, I have acquired the value of phase A, B and C voltages in the notepad here. So I will just paste it over here. Here you go, phase A voltage. Now here we have the value of phase B voltage, minus 315.138 minus J into 55.56. That is the value of phase B voltage. Again, I'm not going to write the whole thing, I'm just going to paste it. And here you go with the phase C voltages. 451.05 minus J into 164.16. That is the value of phase C voltage. So now that I have entered these values, I will be getting the results. Here we have the result for the zeroth sequence, 96.3707. Result for the positive sequence, minus 3.11 minus 1.4. All three values, VA0, VA for zero sequence, VA0, VB0 and VC0. For positive sequence, VA1, VB1 and VC1. And for negative sequence, VA2, VB2 and VC2. Please note here, for the positive sequence, the whole term, the whole matrix is getting multiplied by 10 raised to plus 2, and same I can say for the negative sequence as well. The value is getting multiplied by 10 raised to plus 2. Now if you have a question that why did I took these particular values, why didn't I took any other values, the reason is simple. The just to verify the code is working, I took these values because these values have been taken in our manual as well. So that's why I took the values, just to verify the code is working. And you can match these values, the values which we are getting here, with these values which we have performed the practical for, and you will be able to match them. Hence we can verify that the code is working indeed. So that was it for the seventh practical, in which we have discussed the positive, negative and zero sequence, and we have acquired the values for positive, negative and zero sequence by conducting the experiment, by writing the whole code for it. Now let's clear the command window, and let's clear the workspace. Remember what was the code for clearing the workspace? Clear all. So here you go, workspace is clear. Now we will use CLC. Alright, now that we are done with the seventh practical, let's move on to the eighth practical. In the eighth practical, what do we have to do? We have to do the calculations of symmetrical and unsymmetrical faults. Right, let's first see it from the lab manual. Okay, the question is write a MATLAB program for the calculation of symmetrical and unsymmetrical faults. Now to write these type of programs, you first may have the clear idea about what are the symmetrical and unsymmetrical faults, right? What are these faults, and uh, what are the formulas for calculation of fault current in these faults. So again, this will require the understanding and knowledge of different type of unsymmetrical and symmetrical faults, which we have discussed in the playlist. So again, I will provide the link of that playlist in the description as well. If you are not aware of that, you can check out following that link in the description, or I will provide the link in the I button as well, which will allow you to go to the playlist and check the whole thing out. Now I'm assuming that you're following these lectures regularly, and based on that you understand the different formulas, different type of faults first, and then the formulas for different type of faults. So just to give you a glimpse, there are basically 3 to 4 type of faults. You can say line to line fault, we have line to ground fault, we have double line to ground fault. These are the main major faults which we are going to discuss about. And there was one more, triple L fault. All three lines gets short circuited altogether, right? So we are going to discuss about these 4 faults initially. So first we will start with CLC. We will clear all and then we will write CLC, so that we don't have to write all that in the command window again and again. Close all will close all the files which are here, which are open in the MATLAB. Currently I'm not having any file, so it doesn't matter if I write close all or if I don't write it. Then we will start by taking the input from the user. We will ask the user to enter the value of all three type of impedance. What is the value of per unit positive sequence impedance? We will ask the user to enter the value of per unit negative sequence impedance, and we will also ask the user to enter the per unit zero sequence impedance. Once we get the values of all three positive, negative and zero sequence impedances, we will ask the user to enter the per unit fault impedance, which we will represent with ZF. Positive, negative and zero sequence impedances will be represented by Z1, Z2 and Z0 respectively. Now pre-fault bus voltage is uh, very imperative, very important in this uh, calculation. And if you have seen the videos, we always take the pre-fault bus voltage equal to 1, so EG will be 1.0 here. The value of alpha again is very clear, 0.5 plus j into 0.8666. By the way, the value of alpha does not change ever, so you can even remember it. It's same from the seventh experiment and through, right? So we will take the value of alpha because again we will require alpha. We have seen in seventh practical that for the calculation of positive, negative and zero sequence components, we require the value of alpha. So we will be taking value of alpha here as well in the rectangular form in particularly. You can take it in the polar form as well, but if you do that, then you have to do all the calculation in the polar form. So you can go that way as well. We have taken the rectangular form. After taking the value of alpha, what we will do? We will print. We will print different type of faults. Like we will ask the user to enter whatever type of fault they want to check for, right? So if you want to check for triple L fault, enter 1. If you want to check for LG fault, enter 2. If you want to check for LL fault, enter 3. And if you want to check for LLG fault, then enter 4. Let's do one thing, right? Let's put all these values in new line, right? And by slash n, I think we can do it. Okay, here you go. So everything in the new line. I will quickly save it. Then we will check what is the type of fault, the fault type. So we will ask the user to enter the type of fault. So he will be entering either 1, 2, 3 or 4 because we have asked him earlier, right? Enter 1 for triple L fault. Okay, sorry, I have made mistake here. We don't have to slash n here. Enter 1 for triple L fault. Then we have to write it slash n here. 2 for LG fault, 3 for LL fault and 4 for LLG fault. Now it looks correct. Then fault type will be equal to input enter type of fault, which means we are asking the user to enter the type of fault. Based on the type of fault, he will enter number 1, 2, 3 or 4. Now once he or she enters 1, 2, 3 or 4, what we are going to do? We are going to check. Okay, if he has entered 1, that means the type of fault is triple L fault. If type of fault is triple L fault, then what is the formula for fault current in the triple L fault? Per unit fault current, Eg divided by the positive sequence impedance, right? So Eg divided by Z1 we will take, and the value will be the fault current value will be saved in this variable pu fault current. We are using if statement here, which means if some condition is true, this thing will be applied. If that is not true, which means if the value entered is not 1, because in the bracket we are asking that fault type equal to 1. If and again take a note that we are writing double equal to, which means it is not assigning something, it is comparing it. So enter the value will be, if the entered value is 1, then it will compare it if it is 1 or not, and if it is 1, then we will apply this formula. If it is not 1, then what? Then it can be LG fault, it can be LL fault, or it can be LLG fault. So now let's consider LG fault, which means else if. We will take else if fault type equals to 2. Now once we take fault type equal to 2, the LG fault will be that would mean that the fault which has occurred will be LG fault. Now if the fault occurred is an LG fault, then what is the formula for the per unit fault current? So the for per unit fault current will be 3 into Eg divided by the sum of all three components plus the fault impedance, right? So it will be 3 into Eg divided by Z1 plus Z2 plus Z0 plus 3 into Zf. So it will give us the value of per unit fault current in the case of LG fault. But if that is not even the case, if that is not even the case, then it is a LL fault. It can be LL fault, which means the user has entered number 3. So if the fault type is equals to 3, then per unit fault current will be equal to, what is the value of fault per unit fault current in the case of line to line fault? So it is alpha square minus alpha into Eg divided by the sum of only positive and negative sequence components plus the value of fault impedance, right? So Z1 plus Z2 plus Zf, that will be formula for per unit current in the case of LL fault. Now if even that is not the case, then what is the case? If that is not the case, then it is fault type 4, which means it is LLG fault, which means the user has entered 4. So else if fault type equal to 4, and remember in the case of LLG fault we first need to find the equivalent impedance, right? Equivalent fault impedance, Zeq, and then we have to find the per unit fault current based on Z equivalent. So how do we calculate the Z equivalent? The formula of Z equivalent is also given in the we have discussed in the class, which you can find it from the playlist over there. So it is equals to Z1 plus Z2 into Z0 plus 3 into Zf divided by Z2 plus Z0 plus 3 into Zf. That is the formula for Z equivalent. Now you can print the value of Z equivalent as well. If you don't want to print it, it is okay, it is completely fine, you can skip that part as well. And after that we will try to find the per unit fault current again. The value of per unit fault current here will be Eg divided by Z equivalent. So we will simply write it, and then we will end all these else loops, right? These are basically conditional statements which gives us either or true false conditions, right? Once we end all these if statements, we have to still print the value of fault current, right? What is the how do we know? Because if you don't print it, then it will be saved in the variable somewhere here in the workspace, but we will not be able to see it. So in order to print it, we will use this statement fprintf. The value of per unit fault current is modulus f per unit fault current, right? It is same as we did in the earlier experiments in the third, fourth and fifth experiment earlier in this previous lab session. So we are doing the same thing here. We are printing it. We are taking modulus f because it will be a floating value, floating point values, and in the end we are writing the name of the variable pu fault current. Now there can be one more possibility. If the user has entered something else, something which is not either of these, something different from 1, 2, 3 or 4, like user has entered 0, then what? Then the code will not move forward. So you can add one more if loop which will ask the user that you have entered incorrect value, right? You can do that as well. So I will leave it to you. You can do it by yourself. So let's see who can do it. I will be expecting the answer of this question in the comment section. So whenever you see this video, please try to answer this in the comment section. Please write the code if uh, the user has entered incorrect information, right? Except for 1, 2, 3, or 4. So now that we are aware of the code, let's try to test it and let's see what do we get as an output, if that code works correctly or not, right? So let's try to run it. First, it is asking the value for the positive sequence impedance. Let's enter 0.15 is the positive sequence impedance. Then negative sequence impedance, let's say it is 0.12. Zero sequence impedance, so it is, let's say, 0.08. The fault impedance, let's say it is 0.2. Then it is asking us to enter 1 for triple L fault, 2 for LG fault, 3 for LL fault, and 4 for LLG fault. So we are going for, let's say, LLG fault, right? Because we want to see the value of Z equivalent and then fault current. So I'm right in entering 4. And by entering 4, it is showing me the value of Z equivalent is 0.91160 and the value of fault current is 1.09672. So again, I took these values in particular 0.15, 0.12, 0.08 because I wanted to confirm the code. I wanted to confirm the code works. By the way, don't follow the code which is given in the lab manual. It has errors. So please follow the code which we have shown you here. Don't follow the code in the manual. It is having some sort of errors. I have rectified it in these in this MATLAB session. So you can see here we are having the output and it is matching our exact values, matching with our MATLAB code with exact values. Now let's move forward with the third and last program of the lab session of your syllabus. It asks us to write a MATLAB program for the calculation of disruptive voltage and corona loss. So again, we have studied what corona is and how corona can affect my transmission line. So we have studied corona in detail already. So I'm not going to discuss all the parts of corona in detail. I'm not going to discuss what is disruptive voltage here, but the formula of disruptive voltage I will be discussing, which will be given here, right? So let's move to the code here first. But okay, wait, give me a minute. Let me show you is the what is the formula for disruptive voltage, right? Before you move, because without that you will not be able to understand it. If you have followed the videos in which we have discussed about disruptive voltage, then you would might have some idea. But let me get back to that just to make things easier for you. So here you go. Here you have the value of critical disruptive voltage. Here you can see VC is equals to G0 R log E base D by R. There are few values which you are already aware of. So air density is given using this formula, and value of M0 is somewhere close to this. So you are already aware of these things. So let's go and let's check out what can be the disruptive voltage in this case, right? First we will use CLC and we will use clear all just so we can clear the workspace and the command window. We are taking the diameter of conductor is equals to 10, the radius of conductor is equal to 0.5 into the diameter, which means we are just taking the half of my diameter, right? That's what radius is. P is the pressure of the mercury, which we might require in the calculation of disruptive voltage, if you remember. So temperature is required as well, so temperature will be 30. Air density factor, again we have seen what is the formula of air density factor, delta, which is simply written over here. You can see this was the formula, right? So we are simply getting it in this form here. The value of dl is 2.5, m0 is 0.85. You can see these variables here as well, not here, here as well. We are having m0, the polished conductor, uh, the value of uh, the irregularity factor, right? Irregularity factor for polished conductors as well. So your value of m0 and g0 here as well, so from that we can find the values of these. So here you are having m0 and g0. You know the value of x is equals to dl divided by r. Then we will find the disruptive critical voltage. The formula for a disruptive critical voltage, g0 m0 r delta log of x is basically dl by r, because see here we require dl by r, right? So instead of writing the whole thing together, we just first found the value of dl by r, and then we took the g0 r into log of the whole thing dl by r, right, which we have called x. So g0 m0 r delta into log x, as you can see here, g0 m0 delta r into log x. So that is the formula of my critical disruptive voltage. That will give us the per phase disruptive voltage. In order to find the value of the line to per line disruptive voltage, we will write, we will divide it by root 3. The frequency is 50, the length of my line is 150 meters given. Then we have to find the value of PC, right? The how much corona loss we had, which you can see from this slide. This is the formula for power loss due to the corona, 242.2 F plus 25 divided by delta under root of R by D V minus Vc square into 10 raised to minus 5, right? Where F is equal to supply frequency, V is equal to phase neutral voltage, Vc is equal to disruptive voltage in the RMS. So once you have that value, you can find the value of PC using this formula. Basically we wrote the value of whole formula here, and then we simply printed the value f printf slash n disruptive critical voltage is this much for voltage per phase, and the corona loss is this much, p as much as PC. So and in the end we wrote E0 and PC in order to show the value of critical disruptive voltage and corona loss. Now let's try to run the code and let's see if that works or not. So here you go. So the critical disruptive voltage here is 54.364 and the corona loss is 373 kilowatt. Let's see if that matches the values in as per our manual or not. So the see the values are matching, 373.004 and 54364. So you can see the values are uh, matching in experiment and manual. Now there is one more practical which discusses about let's see 10th one, the which discusses about the MATLAB based simulation of uncompensated transmission line. Basically this is the experiment which is performed under Simulink, MATLAB Simulink, and you just have to. I have given this circuit. I expect from you to form this circuit in MATLAB Simulink environment. You don't have to do anything. You just have to go to the MATLAB Simulink. You have to just simply open the uh, directory or open the part from where you can search these different sources, these different things, and you just have to connect it, enter the correct values of resistor, inductor, and run the circuit, and you will get waveforms which will look like this. So I expect you to do at least these, at least conduct this practical on your own. If you face any doubts related to this practical, please tell me, approach me. You can write them down in the comment section below as well. So I will be expecting you to do it on your own. If you have any query in that, please ask me. So we will keep this session till here. If you have any doubts, any queries related to this session or any other thing, you can mention that in the comment section below as well. I will try to answer your questions and queries as much as possible and as soon as possible. And please, it would be amazing to see you guys giving feedback about the channel, feedback about the lab sessions, and even the lectures. So any feedback will be very much welcoming, and we will keep this class till here. So thank you very much for listening. I will be signing off, and I'll be seeing you next time with new video. Thank you very much. Goodbye for now.